On behalf of the board, I want to welcome all of you to our 10th annual Developers Workshop. So without further ado, I want to introduce our keynote speaker, Dr. Thomas Stirling. He is a professor of informatics and computing at the Indiana University. Quite established. He authored half a dozen books, several patents in this field. He is the father of Beowulf. For those of you who have been around in HPC are familiar with his work. For those of you who are not, you are in for a treat. He is going to talk to you about the phase changes of exascale computing. And so without further ado, please welcome Dr. Stirling.
Good evening, ladies and gentlemen. And it is a delight to be here. It's even more delightful that the weather is not like yesterday. Almost got washed out. In the next few minutes, I have a very simple message that I want to discuss, and that is the trends that are taking a sharp turn in the field of high-performance computing. This is the sort of thing that one can hear often, indeed. For those of you who have been around as long as I have, you've heard it almost continuously for the last 20 or 30 years. I hope to convey to you the reasons for and the nature of the changes that are about to take place, and indeed that are taking place, at least in the applied research community. The exascale computing is at a position, really a point of inflection, where innovations, to a degree we've not experienced for the last 20 years, is essential. And I will show you reasons for those changes. And those changes will be across the board. They'll involve computer architectures, parallel programming models, and system software. And this is not good news for a lot of reasons, but it will prove to be essential. So in fact, over the next 5 to 8 years, and even at this point, the vision is a little fuzzy, there will in fact not be a future high-performance computing platform or a future exascale machine. But in fact, there will be two largely different such platforms, different classes of computing that will be going forwards simultaneously. One, and my terminology is probably inadequate, but is the evolutionary path or incremental path from those structures and techniques with which we are very familiar and heavily invested today, and invested into the near future based on vendor roadmaps as well as the user community. But the second, and again, poor terminology, and I will use it, the revolutionary approach, a more accurate term, but clearly not good marketing, would be the disruptive approach. The reason I have trouble with the term revolutionary is, indeed, if applied, it will be revolutionary in our usage, but it's not revolutionary in a set of ideas. Indeed, as you will see, a number of these ideas that the research community is pursuing go back 10, 20, even 30 years in certain cases. In order to achieve this revolutionary or innovative approach, we're going to have to break with the past and adopt not just a new architecture, not just a new programming language, but indeed a whole new paradigm, an execution model. An execution model that will address the challenges, as I'll describe later, that impact the efficiencies and scalabilities of the machine, and that exploit dynamic and adaptive techniques which, while certainly have been found in other disciplines within the computing arena, have for very good reason been avoided in the past in the field of high-performance computing. And I'll just say so here, it's understandable because the idea of using dynamic techniques, which are embodied and embedded in a combination of hardware and software, actually add more work to a computing stream that you would like to actually shorten the execution time of. Well, this is the you are here picture. On your left is Tianhe 2, I mispronounce it, probably Tianhe, I'm told, means Milky Way, not the candy bar, it is the galaxy. Tianhe is about 32 petaflops of sustained performance on the LINPACK or HPL benchmark, in excess of 50 petaflops peak performance. It has a relatively small memory, and it combines a combination of regular Xeon parts with the Xeon Phi, densely populated lightweight processor cores simultaneously. It's interesting, Tianhe 2, the name may suggest to you that there was a Tianhe 1. There was, in fact, it was Tianhe 1A. There was never a B, as far as I know, and that also used Intel parts, but to increase the peak performance at least. That machine had previous generation NVIDIA parts. Tianhe 2, as measured and when measured by the HPL benchmark, is currently rated as the fastest machine in the world. The fastest machine in the US is Titan. Titan is at Oak Ridge National Laboratories, and it's about half the performance, half the cost, and slightly less than half of the total power. I didn't mention the power. Including cooling, Tianhe 2 consumes 24 megawatts. And to put that in perspective, it's asserted, somewhat arbitrarily and subjectively, that the highest power consumption that you would want to tolerate for practical purposes for an exaflops machine would be about 20 megawatts. So this is my beginning to address some of the concerns we have. One last thing I'll say about Tianhe 2. Obviously, if you're linear-minded, 32 petaflops doesn't sound like it's a long way to an exaflops. But if you are, as I suspect many of you in the room are, if you're rather base 2 logarithmically minded, then it's halfway, right? That's 2 to the 5th petaflops, and we would want 2 to the 10th. And by the way, yes, I'm entirely conscious of the fact that finding a particular point in the execution continuum is indeed arbitrary. We tend to use tri-decade ranges of performance, and so Exascale is not indeed considered a single operating point of 1 exaflops or 1 exabyte or 1 exabits per second, but rather a regime from 1 to 1,000 exclusive of the performance regime. I have been quoted, not with the most positive response or reaction, to state, we'll never get to the other end of that regime. And I'll say more about that later. So for our first consideration, and because of the interests of this audience, I bring to your attention that the class of machines we talk about are shown in this cartoon. And really the only point that I want to make, yes, it does show multi-core parts. It shows the memory broken apart, fractured from the rest of the system. It shows 1 or more accelerators within each node. Most importantly, it shows merely an ensemble of nodes where principally all of those nodes as perceived by any other node is just part of the I/O space. Now when you think about it and consider the level of computation resources that will be required at the scale of exaflops on the order of 1 billion threads, and I'm probably being conservative here, you realize that that means just about every core, modulo a small number of powers of 2, just about every core thinks of every other core in that system as an I/O device. This is not the semantics that the application programmer wants to consider. Now, principally this talk is going to bash the conventionalists, the incrementalists. But let's be fair, not only are they being very professional and very responsible, there's a very good chance that to first-order approximation, they're right. After all, this is the techniques we're talking about have been employed for the last 20 years with extraordinary success. Indeed, in the field of high-performance computing, probably the single most successful, well, the second most successful idea has been captured by the communicating sequential processes model and its representation as the MPI programming interface suggests. I said second most successful because there's an underlying but very important assumption that has largely driven the rapid inflation of perceived performance advantage, and that is the notion of weak scaling. That increased performance with larger resources comes by increasing the problem. Now, I remember when my friend John Gustafson, I think working for Shell or one of those oil companies, first published this paper. I looked at it, and in those days, this is days of craze and SIMD machines, so thought it was a fraud, but in fact it was actually deeply insightful and of real value, because at that time it wasn't about the flops so much, it was about the bytes. And we really did need larger problems. So in a sense, what we've been experiencing is a period not of increased performance, although that is a side effect. It's been an increased memory size or data set size. The notion of big data is not new to high-performance computing, even if it is new to the hype and energies of those who want to jump on the next bandwagon. The incremental approach has leveraged quite successfully Moore's law, and indeed we have been riding an S-curve for the last 20 to 30 years. The premise of this presentation that we are now going over the top and we are moving out on the asymptote, on the anvil of the S-curve, and this talk is about those implications. Can't give a talk about high-performance computing without showing at least one plot of the top 500 list, the 500 fastest machines as measured when they're measured using the HPL benchmark. The red line there is the #1 machine. You can see it's pretty much a sawtooth. When a big investment of $1 to $200 million in whatever currency of the nation is invested, hopefully that machine stays at #1 for some time. There's very much a stature factor involved, unfortunately. However, some of those machines have also done some very good science. The green line is the 500th machine in there, and there's usually approximately about 2 orders of magnitude, again, measured in this Rmax value of HPL. According to the extrapolations of this chart, and you can see it for yourself, it suggests that by the end of this decade, there will be in place 1 or more exaflops Rmax machines. If I may comment, I don't anticipate that that first machine will be in the US. I could be proven wrong. I'm perfectly happy. But in either case, whether or not it is, it doesn't mean it's a machine worth building or owning or paying for. It means it's a machine that runs LinPack, exaflops. Now, I'm occasionally asked, do we need exaflops? I mean, after all, and this is quite valid, much of the workload, much of the workflow is of a stream-like or embarrassingly parallel, to use a phrase I've never quite understood. And why do we need an exaflops machine? Why can't we just have 1,000 or 1024, I guess, to be more accurate? Why can't we have 1024 petaflops machines? After all, a Russian company, RSC, has implemented a 1-rack petaflops peak machine. It was just produced over the last year. Now, you know, the rack is a little bit wider, it's a little bit taller, and it's a little bit deeper than what we all have come to think of the standard rack. So maybe they just made a little better. It is loud. The fans pushing the air over the liquid cool. Oh, and did I mention the power? 1 rack, 400 plus kilowatts. Nonetheless, there is this density. So I could, of course, give a whole talk, and I could, with great sincerity and passion, tell you about modern civilization destroying the planet, but we don't understand. We can't even agree that we're doing this, depending on the color of your voting ballot, I guess, right? The need to be able to manage or to produce or predict global climate, is essential. Well, let me just choose a problem that I particularly think is important. And that has to do with the same topic I just talked about, right? Energy, and where we're going to get it, and all of the implications and side effects of the way we get it, right? I should be more sympathetic about birds getting sliced in two by large windmills, I suppose. But in fact, you drive up whatever your favorite interstate is, you go through a windmill farm, and the blades aren't turning. And you ask, why aren't the blades turning? Because doesn't that mean there's not going to be a lot of power? And they say, well, one of two things. They say, there isn't any wind. Or they say, there's too much wind. And there's a time you have to turn it out. Well, I'm a kid from New York City, right? And the reason I tell you this is because there is one generator called Big Alice, and Big Alice is over 1,000 MVA, 1 gigawatt machine, one generator, 1 gigawatt machine. Those windmills are somewhere in the range of 1 to 5 megawatts, which is pretty impressive, actually, when you think. But think about the real estate you need to replace that one generator in Queens, New York, right? You got to really have an impression. A different approach might be the use of the same power, the same mechanisms that create all of the light in our galaxy. That's to say, the fusion in the stars and control fusion. Well, control fusion has been what do they say? It's a promising technology, which is to say it's always promising. But in fact, incrementally, slowly, decade after decade, progress is being made. And the ITER, the International Thermonuclear Experimental Reactor, I knew I'd get it, actually being constructed in Grenoble, France, I think. International Japanese are doing much of the computing, but we're doing some of it too. And the problem of both simulating and controlling the future of thermonuclear or fusion reaction is very complex. It's multi-physics and it's multi-scalar. It's highly nonlinear. And this problem is, in fact, an exascale computation. To deal with all of the different challenges working simultaneously. I mean, just imagine this. These things have turbulence, like little tornadoes in the middle of these plasmas that are 1 million degrees. It doesn't matter whether it's Fahrenheit or centigrade. When you're talking about 1 million, you don't worry about 5 nines, right? But these toroids, they're viaducts to move energy and mass away from the center of the core where you're trying to contain and out to the sides, and therefore dissipating the energy. And just to be able to quench such turbulence, you need to control a combination of toroidal and poloidal coils, and I don't know which is what, just to wrench the plasmas apart so that these turbulences go away. And that's just one of many problems. Now, I talked about the top 500 list. And this is really the same set of curves. The red one is number 1. The green one is number 500. But it's a misleading curve. That 2 orders of magnitude, you would assume, you'd expect that somehow all those 500 machines would be roughly uniformly distributed across that range. Not so. So very much not so. A colleague of mine, Maciek Brodowicz, at my request, did an analysis of what is the typical supercomputer. I don't even know what that means. What is a typical supercomputer? So in a classic data mining, trying to find various patterns in the data, multidimensional data sets, produced the yellow line that you see here. Now, out of the number 500, the yellow line tends to be somewhere on each point, somewhere between number 65 and number 70 of all the 500, where number 1 is the fastest machine. So that yellow line represents more than 80% of the fastest machines. Okay, between the red and the green, about a factor of 100. Between the yellow and the green, at least except at the two ends, about a factor of 2. So for all intents and purposes, almost all of the supercomputers that we measure are in that tiny little sliver. And then you have a few of these big machines. Some of them important machines, some of them stunt machines, but the last few are about less than 20% are there. So our notion of supercomputing becomes very warped when we just look at some of the data in the more averaging or broad sense. No, I have to concede that if you draw on a number of factors and say these are the practical constraints of exascale, any one of you would have the right to ask, really, aren't those the constraints of petascale? No. For an example, you can read this. I'm not going to read all of them. You can worry about cost and so forth. But let's go back and talk about that question of generality, this notion of weak versus strong scaling. Strong scaling, when I was young, was what supercomputing was about. How does performance increase? It increases by doing the same work and reducing the time to solution. Until, again, John came. And by the way, it was John who coined the terms weak and strong scaling in the seminal work that they did so many years ago. But here's the problem, and we'll get to the details in a moment. Supercomputers are becoming less general, not more general. More and more problems are unable to leverage the compute performance that are provided by these machines. And this is why, as we approach exascale, why we think about the next 2 to the 5th, 2 to the 7th advantage in computing, we find that we may be building machines that have almost no purpose at all. Let's look at why. Okay, from my colleague Peter Kogut, University of Notre Dame, and he did this originally under DARPA contract when DARPA cared about high-performance computing. They don't seem to anymore, unless it's in a drone or in a satellite or in something that crawls along the ground from iRobotics or whatever. This shows you over the last 20 years the way the power has been used and how it's been rapidly increasing. Now we're at a breaking point, as I've already indicated. And so increasing the power is no longer a viable approach. Well, what's proportional to power? It's clock rate. And so we see that over the last 8 years or so, the clock rate of processors have basically flatlined. One of the most important ways in which over the previous 20 years we have gotten and derived an increase of performance from the cores, from the processors themselves, those no longer happen. By the way, the other approach has been through architecture. Architecture itself hasn't so much given us that much more. It's enabled the technology to be exploited, but one way it has is through the amount of very fine-grained parallelism, instruction-level parallelism. There were times back when ILP was first being touted, well-intentioned people. This is, I'm a professor, but I haven't always been a professor. And so there are moments when I just don't think that academics get it, right? So academics love lampposts. And by that I mean they love to look under the lamppost where they're going to find the answer they want. I know that's unkind, but you can go back, Google it, you'll find papers that talk about 1,000-way ILP. And it's true in certain problems, but in fact, when you actually measure real problems, such as controlled fusion or climate modeling, you'll find that the ILP is somewhere between 0.5 and 1.5 on average. Okay, between 2 and 3. All right, you're being too kind. But then the people I'm talking about with those papers aren't very far away from you, Jeff. So they're just down the street. The total concurrency of the machines, and by this we mean the number of cores, whether they're just simply left as an ensemble, such as multi-core chips, or rather that they're organized in certain structures, such as things like, but not limited to, the accelerators, GPUs that NVIDIA provides and others, is now growing exponentially. The colors on this graph, your red dots are principally the x86. Your green dots here are blue gene. Now, it's interesting about IBM, right? They had two classes, actually 3 classes of machine. I was at a talk 2 weeks ago in Switzerland, and Dave Turk explained why getting rid of divesting themselves of their entire x86 portfolio was morally the right thing to do. Well, I remember talking to one of his colleagues, Tilak Agarwala, a mere, 15 years ago, having breakfast, when I was telling him that x86 might be the right thing to do. I don't know if IBM undertook that path because of what I said, but they did, even embracing Linux as a possible medium in spite of AIX. AIX costs about $100 million a year to maintain. And Linux has a better approach. They don't maintain it. I mean, if you don't like it, fix it, right? Ravi Armilio at Austin, the power architecture. Really, it's a tour de force, right? And they pretty much alone have pushed the power and the clock rates up into the 3 to 4 gigahertz range. They exploit speculative execution to the point where there's more than 100 operations in flight at any one time. It is truly an exceptional architecture that I anticipate is doomed. This isn't being videoed, is it? He said, staring into the lens. All right, so the technologies that we're seeing are now pushing us into a point where the parallelism is at a different level. It's a medium-grained level. And the weaknesses we're experiencing, we just talked about the percentages of efficiency, which frankly find themselves but lower than 10% for many of these real-world problems. And usually there's somebody in the audience when I say that who laughs and says, yeah, I wish I could get 3%. Now, in fairness, it really depends on what you define efficiency to be. But the scaling that we face using standard techniques is limited by the forms of parallelism we're using. We're using either coarse-grained parallelism, MPI processes, on a scalable machine. Yes, OpenMP, medium-grain threads, but on an SMP, which is limited in scaling. And these machines are particularly bad for strong-scaled applications. In fact, for strong-scaled applications, Moore's law has become irrelevant. Moore's law is dead for those problems, and those problems are important. I mean, for example, the whole genome mapping problem, or even more importantly, but in that sphere, modeling at the molecular level the interaction between cells or large organic molecules and the cells, penetrating cells' walls, may even require the modeling at the quantum level. These problems are stuck in the range of a few thousand cores, yet the Tianhe 2 has 3 million cores. Moore's law is dead. The factors that contribute to this challenging situation, I codify it as this performance degradation. And I use the term slower. It stands for starvation, latency, overhead. I got into trouble in the next one. Waiting for delays due to contention. Okay. And the last two weren't even mine. One is energy and the other is reliability. But they all come out to the same units, which are time. This formulation of average performance includes the issues of efficiency and scalability. Takes into consideration the implications of power energy for clock rates, and also worries about the practical considerations of reliability in contributing to availability of machines. What is your mean time to interrupt? What is your maintenance time? And so forth. Let me quickly define terms. Starvation, as you can imagine, is simply the inadequacy, the insufficiency of the amount of parallelism or concurrency that's available for the computation. Now, this can be due in absolute terms. There simply isn't enough parallelism in the algorithm, and I'll show you some results shortly that suggest that. But it also could be bad load balancing, where some things just don't have enough work to do, but others have too much to do. Latency, that's a distance. And the RDMA community is very familiar with this. This is a distance usually measured in cycles for remote access or remote service requests. Overhead is the insidious one. Not only is it just wasted time and wasted energy, as well as wasted cost, it puts a boundary on the granularity of the parallelism that you can effectively exploit. And so here, this demonstrates that these are not our, unfortunately, these are not our orthogonal parameters in consideration. And finally, the contention, which contributes to the problems of asynchrony and therefore uncertainty in computation, just to aggravate some of these other factors. Now, our conventional practices putatively address these problems. In the cases of overhead and latency, they address them largely by avoidance. They support such large parallelism, such large granularity, that it mitigates or just overwhelms the amounts of costs in overhead and latency, and they do so through static task scheduling, static organization, static allocation of resources. And if the work is uniform and regular and coarse-grained, and we don't try to get too much parallelism out of it, it actually works very well. And it's been the reason for much of the success. Let me just show one curve. This was done by, I didn't even give credit, my colleague Matt Anderson, a numerical relativity person. I'll show you some additional results of his later. This is an n-body code called Gadget, written in MPI, widely used, also is used for smooth particle hydrodynamics. In this, I wouldn't have chosen the colors, but red is good. It means we're processing. Blue means something hasn't happened. The vertical axis is just an enumeration of the various threads. So there are 128 threads on this diagram. The picture speaks for itself. Using a software layout, bulk synchronous parallel, popularized by Leslie Valiant of Harvard, you see that it is the slowest piece of the computation in each phase that moves, that determines the rate of the execution. And you also see an enormous amount of time when the inner loops of the threads that are being executed and exposed for parallelism are irregular, are non-uniform. And this is typical of many calculations. So we organize our computation to do the poorest it possibly can, and in that we succeed. But there are other approaches. My colleague Jack Dungara at the University of Tennessee, he is, although with other colleagues, the father of, among other things, the LINPACK benchmark, but many other contributions. Has developed a linear algebra package in using a runtime system, a dynamic runtime system, and conveying the precedent constraints of the computation in terms of a DAG or a directed acyclic graph. This is not a new idea by any means. Indeed, the use of data flow synchronization goes back to the 1970s, Jack Dennis and many, many others, and for a period of many years. Work also at Barcelona Supercomputing Center, something called STARS, also uses this. But nonetheless, Jack's work and that of his team shows here that by recasting this linear solver, he's able to get slightly better than a factor of 2 by allowing the machine to self-adapt. I and a number of collaborators in the US have been developing an experimental model, an execution model called Parallax, for the purposes of research to explore the integration of a number of key concepts that permit the exploitation of dynamic adaptive control, again, for efficiency and scalability, using such things as control for data flow representation, using concurrent threads that can be preempted, therefore avoiding non-blocking, using message-driven computation, the ability to send data to a remote site efficiently, or to, in fact, invoke an action at a remote site near the data on which it's going to operate, thereby both reducing and hiding the effects of latency, and using much more powerful than the global barriers I showed you a moment ago, using very rich semantic synchronization objects, again, first explored as many as 25 or 30 years ago, such as data flow in futures, and doing so not in a distributed namespace, but doing it rather in a global namespace, which means that you can communicate to the machine your intent rather than having to coerce it to do the right thing. Here is, again, from Matt Anderson. This is another code, this from the Department of Energy, for hydrodynamics called Lulesh. It's a mini app that is widely employed and represents a larger code also in the national labs at Livermore and so forth. And on your left, you have the MPI version, which has been heavily used, and this recast as a code using these asynchronous techniques, these message-driven techniques of Parallax. We've implemented these concepts in multiple versions of a runtime system called HPX. I don't even know what HPX stands for, sort of highly parallel or high performance, parallax or not. But anyway, some mix of words like that. HPX becomes its own name. And you can see that these effects, these results from the global barriers are not just mitigated, but eliminated. So the class of machines that we're now talking about, let's just put it under the Parallax umbrella, but indeed others have worked on various parts of these ideas and are currently working on them as well. I should note the work at Lawrence Berkeley National Labs, Kathy Yellick and her colleagues on such things as PGAS and GasNet, Vivek Sarkar and his work on Harbonero C, the work at Illinois by Sanjay Kali on Charm++, and there are a number of others, but they're not giving the talk, I am, so we're talking about Parallax. The only thing that's important about this cartoon versus the original one is the heavy dark line. Now, all of the computational elements are logically and physically in the same global namespace, which allows not just the data, but the actions themselves, those actions, whether they're processes in the large sense or threads in the medium-grained sense, are also first-class objects. That sounds sort of academic, doesn't it? But it's very important. It means that now, not just the text of a task, but rather the very execution of the task can be managed dynamically by the runtime system because it can be named. So this brings us to a point where we compare these two coexisting classes of systems that will move forward. And I won't read all these, but I'd like to pick a couple of them out. Let me take the first one there. The one thing that they have in common is change. So if someone were to say to you, we want to continue to use MPI, they're right that that's what they want, but they're lying if they're suggesting that's what they're doing. MPI 3 has been released as a specification, and indeed, MPI plus X is the vernacular term for we'll take MPI, but under that we'll throw something else. Today that's usually OpenMP, but OpenMP doesn't know about MPI. And they don't stop there. because after all, they've got these heterogeneous accelerators. So then under MPI, they're calling, guess what, CUDA or OpenCL or OpenACC. So whatever we do, whether it's incremental or putatively revolutionary, it's change. You see as you move down that we're moving from a synchronous representation of the problem to an asynchronous representation of the problem, where the system can adapt to the uncertainties of asynchrony. In fact, and this is not my point, this is others, that you can actually exploit those for taking advantage of getting better utilization simultaneously, not only the processors, but the memory bandwidths and the memory access bandwidths and the networking. And by the way, it is data movement that costs most of the energy, not the processing itself. So let me just show this simple example. See if this works. Okay. All right, this is thrilling. Are you thrilled? All right, let me tell you why you should be thrilled. Okay, so on your right is a picture of LIGO. LIGO is a laser interferometric gravitational observatory, not one but two, one in Louisiana and the other in the state of Washington. Its intention is to measure gravity waves. Now this is, I'm told, the most expensive project the National Science Foundation has ever sponsored. And after 10 years, the scientific results have come in, and the number of gravity wave observations it made is, let me remember now, oh yes, 0. Okay, well 10 years, a lot of money, there are a lot of starving faculty who would just like a few dollars for the graduate students, so the NSF did the responsible thing, the thing you would expect. They threw more money at it, so they can measure 0 to more significant digits. Okay, now, the reason I'm telling you this story is because I didn't get any of that money. And because in order to get the sensitivity, the signal to noise ratio up, you have to decide what you're looking for first. And you do that by simulating, such as I've just shown you on the left, simulating. This is an abstraction of two neutron stars in mutual orbit around each other. What you can see that this is an adaptive mesh refinement algorithm. And what you can't see is that they're getting slightly closer together. Where does that energy go? Is it due to tidal forces? Right? And where does the energy go? It goes into gravity waves, which we haven't seen yet. Of course, many of you will have seen the recent reports looking at using a completely different technique, looking at the background radiation of about 380,000 years after the Big Bang. They're now able to detect a gravitational wave signature in that microwave somewhere around 2.7 kelvins, which is just truly amazing stuff. I mean, it's Nobel Prize winning. Now the reason why it's not quite as important, by the way, and I'm going off, I'm going rogue right now in this talk, but I just have to. Not quite as important as the discovery by Berkeley scientists, also using supercomputers, some dozen or 15 years ago, that the universe itself is not slowing down, but in fact speeding up, is because that wasn't even predicted. This was actually predicted, so you can decide which is more important. But in either case, we're a little bit closer to understanding the universe in which we exist. There is another problem with the idea of finding the signals you're looking for. All right, I don't know if there's anyone here from NASA, but I worked for NASA for 14 years. Point I didn't tell Bill, and they were studying the ozone of the Earth, and they had one of these little application-driven filters too. And when the data was anomalous, pathological, well, you filtered that out as bad data. They filtered out the ozone hole, was only the Brits going over the data some years later that they actually found out we were doomed, or at least the Penguins were. All right, so here is a slight variation on what I just showed you, and this is actually the money shot. What you're seeing here, I've never been able to explain this very well, but on the horizontal axis is the physical time of the computing itself. The vertical axis is the simulation time. Ordinarily, using the bulk synchronous parallel, the simulation time is one curve that you do each phase one at a time. What is really extraordinary about the kinds of techniques that Jack Dongarra uses and the techniques we're using with the Parallax execution model and running HPX is that we, by eliminating those global barriers, are not only able to overlap the computation with the communication, thus hiding latencies, we're able to overlap the computation with the computation, and with the computation, and with the computation. We ourselves, for some of our applications, have seen upwards of a dozen different phases of the computation overlapping, therefore exposing much more parallelism and both giving us more scalability and overlapping and hiding the effects of overhead and contention and latency, thereby giving us much more efficiency. This was really rather spectacular to see this, and it informs us as to how future systems, architectures, programming interfaces, and the system software in between must be refactored, recrafted in order to exploit this. Now, this is not easy. I'd like to show you, and I don't usually do this, but we're like friends, right? Okay. I've known you for 30 minutes or so. I'd like to show you some bad results. But they're not bad results. They're bad results if I were trying to sell you a product. They're really good results if you're trying to do research in order to determine how to move forward and how to give us some machines. This first one, and ordinarily I'd be really embarrassed to put these pictures up because these are Fibonacci. Anybody who throws up Fibonacci, you immediately know they're a junior faculty member or a graduate student or someone, right? You don't put up Fibonacci. This is just humiliating, except Fibonacci has one redeeming value. It's worthless. Okay? It does nothing. And so if you are running something that does nothing, you would like it to take no time. And when it does take time, it exposes the underlying fabric of the computation, the overheads and the effects of latency and contention, as well as the availability of the parallelism. Now, we've done a number of these comparisons. It is a good workload, very simple workload, to exercise the machine very rapidly and expose the limitations. We have two different versions of HPX. One done back, it says, December of 2013. It wasn't that long ago. And then the current one we've been running. So this data is only about 3 or 4 weeks old. It shows that we're very proud, a dramatic improvement on the order of 2 orders of magnitude of our latest release versus our earlier work, and also in comparison to some other software packages that are being used. The picture on the right, however, gives us a little bit more humility. Compared to systems, and now I have to look at this myself. You can see it. I think it's from Intel Silicon TBB, which have been optimized, but this is running on an SMP, symmetric multiprocessor, shared memory machine. And we're somewhere in the order of a factor of 6 or 8 poorer than the best tuned systems. But this is, to use a cliche, comparing apples and oranges, because the threads that are running under TBB and Silk are not scalable. They'll live quite happily on a shared memory node, maybe up to 64 cores, but they won't. Putting Mike aside, sorry about that, but they won't scale to 1 million cores, and we have 1 million core machines today. Here's another one. This is even more difficult. Instead of even executing a code, we're just looking at the overheads and other aspects involved in just creating and spawning threads. In parallel, where we're doing many threads at the same time, we're very good. In fact, we are among the best systems. But if we were just to sequentialize those, because these other properties are not required by the other systems, because scaling actually, so that strong scale problems can run on 1 million cores, there's more work that has to be done. And that also includes the global namespace. And finally, here's another example of Lulesh. I show you this one because there's a fundamental problem that we face. And I don't think there's any way around this. And it has to do with the algorithm. So here are two curves, the MPI versus our version of it, but we use the same algorithm. In essence, what we're really just doing is we're taking our overhead-ridden runtime system and trying to go back to back with comparison with the MPI statically scheduled system. And the green shows waiting times involved in this. So it's more than just rewriting the codes. It's reconceiving of the codes that we face. The problem that this nation faces, indeed the entire international community, is no one problem. It's not like we need a new architecture, we do, or a new programming language or interface, which we do, or we need the right runtime system, which some people think is the answer. No single runtime system is like do. But we, in fact, and we as a nation are currently exploring, without going into detail, exploring these 10 different issues to build new programs, research programs, over the next 1 to 5 or 8 years as we move forward. Understanding actually what embodies these problems is not always clear. The penultimate one on that list, productivity. Productivity, in fact, is perhaps the single most important parameter or metric that we have in high-performance computing. And yet, you can't get anyone to tell you exactly what it is, let alone give you what the units are. I've explored this space personally under previous programs as much as a decade ago, and so I have some feeling for the challenges that we're facing with it. But these are problems that now have to be adequately addressed. So in conclusion, the points I've been trying to make is that we are in a new phase change. It's not the first time that our field, high-performance computing, has this. I count, your history may be different, I count that there have been 5 previous ones since the dawning of the von Neumann architecture vacuum tube era, and currently, we're in the 6th phase change, and that the next decade of HPC will have to be as revolutionary as the change to vector computing, or the change to SIMD computing, or in my own area, the change to Beowulf clusters. Very big, all just as disruptive as what we're facing now. Parallax is an example of the paradigm, of the model of computation that in all likelihood will at least represent the forward-looking systems, recognizing that they will exist concurrently with incrementally advanced systems from past practices. And the early experiments are proving encouraging, at least for those class of problems which are already off of Moore's law, off the exponential growth. So with my few gray hairs left, I'm working the current problems in what we call the neo-digital era. But even when we flatline, even when we hit the asymptote, when Moore's law runs out of atoms and Boltzmann constant says no more power, and the speed of light insists that it's just going to chug along at the speed of light, there are other truly imaginative, innovative ways that are already being explored. And I think you will share with me the notion that whatever we know, what we don't know is far more interesting, and the future will be fascinating. Thank you very much.